Morning, everyone.
Good morning.
Okay, so there we go. Our usuals. Okay. All right, I guess it's time to share screen. Yeah, we're starting right off today because we got a lot to do. Okay, here we go. All right. This last time we completed, I think we completed the sheet except for the periodic table, right?
That's right.
Okay. So we're going to do that today. We're actually going to complete that part. I was kind of hoping to do that in person, but it works okay like this. So here we go. All right. So we're going to go all the way to the bottom. And you can see it, but let me flip it around so you can actually see it better. Okay, there we go. All right, on here, it tells us to number the groups. You see that? Number the periods. Okay, so we're going to do that. Basically, the groups, we're going to, oops, where did you go? Sorry, I am trying to get it down there. Okay, there we go. Number the groups and the periods. So we're going to number the groups first. And to do that, we're going to go across. We're going to number them twice. The first one's just 1 through 18, so it's easy. You guys can do that yourselves on yours. But the other part, it's a little more complicated. So we're going to start with here with 1. Oops, I wanted blue, not red. The red one's going to be the different one. Okay, so 1. Yeah, I know it's so simple, but it's just so that they match. That's all. 3. I can just keep going with this one since it's all one long thing. 4. Oops. 6. 7. 8. I think we're just not moving. Okay, hold on. Keep going all the way to the end. Okay. 10. 11. 12. And now up here, we got these to label. 13. 15. 16. 17. And the top one we have to label by itself because it's up there in 18. Okay, so that's the normal labeling. But the one we really use the most is this one. So this needs to be in red. Hold on. Let me make it red. Come on. Okay, 1A. It's going to be the same except you're going to have an A with it, and it is not going to go in the middle until later. So 3A. And again. 4. A, 6A, A, and then of course up here it's 8A. Okay, now the middle area are B's, so we're going to start with those two. And they are, it's weird because they don't start with 1B like you would think. Instead they start with actually 3B. 4B, 5B, and then there's a lot of 6Bs. Oh, sorry. Did I say 6? I meant 8. Sorry. You know, my brain's not working today. Hold on. There we go. 8B, 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 8B. This would be, there's no 9, so it's 1B, back to 1B, and then 2B, which is really strange. I know. That's the way it works on this periodic table. Okay, so that's those. Now, as far as the periods go, these are all the groups. We have labeled the groups because they're on top of each column. So that tells you which one's which. And then the periods, we label them right next to the rows. Hold on, I'm trying to get this row in the right spot. Okay, so that'd be 1, and then 2. I'm gonna put them not so 3. Yeah, like that. There we go. That's how I want it. 4. Six. Okay, well, that one did. That's okay. Just put it on the side. Okay, and that's 7. All right, and that's all of them. I know they're not perfect, but all right. So that's your rows and your periods. Your periods are, I mean, your columns, sorry. Your periods are your rows, and your columns are your groups. And you might hear me say it backwards, but that's the true statement right there. Periods are columns, rows are groups. See, I did it again. See, I told you I would do it. Periods are rows and columns are groups. There we go. Thank you. All right, the next thing that we need to do is label all of the columns that we've labeled. So I'm going to actually give you a labeling up here so that you know what they are. So 1A is known as the alkali metals. Oops, I don't want them all. We don't want them in capital. Looks like I'm yelling at you. Okay. I don't like that. Okay, 2A. And that should be capitalized. Okay. Is the alkaline earth metal. Oops. 3A is the, they don't really have a name, but they're also known as boron group. There's borons on top of them. And 4A doesn't really also have a name per se, but we will call them the carbon group. Okay, that's all of those. And then we have the rest of them, which I think will fit here. So 5A is known as the nicogens. 6A is known as the chalcogens. 7A is known as the, oops, there's an A there that I did not put on there. There we go. 7A is known as the halogens. And of course, the last ones, 8A, are the noble gases. Okay, there you go. You got all your labels now. And you can put them on there directly, excuse me, or you can just do them like they are. Now, there are more things to label. And for that, I want to do them on top of each one. So on top of this whole area, this whole entire B area, these are known as transition metals. Metals. Okay, for some reason. Fingers. Just gonna put them right in the middle, like that, maybe. Okay. And then down here, these are known as two names. They have actually two names, so they're gonna be known as inner transition metal. Oops, too many ins. Inner transition metals, or rare earth metals. Okay, let me make it a little bit longer so you can read all of it. Okay. Transition, yeah, I knew there was a, there we go. All right, so that's them. Now, the column that I'm pointing at right here, these are known as the lanthanides. I mean, the row, I should say. That's not a column, that's a row. And the bottom one is known as the actinides. Okay, and that's all our labels that we need there. All right. Now I'm going to remind you of that little stair step that we did before. And I'm going to draw that one in black. Yep, black. And it's going to go in the boron group. So I'm going to have to draw it with my finger. Otherwise, it might look really weird. Okay. All right. So to the all the way, and I'm going to circle everything that is a metal in yellow, just so that you see it. So everything that I'm, and of course there will be some exceptions, and we'll start those, but basically all of this, right? Everything here, all of this, all of that, all of this, all those are metals, okay? Except for, oops, I did put hydrogen in there, and I did not need to put hydrogen in there. So except for hydrogen, hydrogen's not. But hydrogen's tricky to put it over there, so I'm just gonna leave it as not a metal. It should actually cross through here. If we can erase this area, that would be good. Ah, not what I meant to do. Let's undo that. Okay, so we'll just leave it alone. We can't just erase it, because if it erases the whole thing. All right, but just cross it through there. Okay. And then the other ones, which are the non-metals, we're going to put in, let's say, blue, like turquoise. Let's do that one. Okay, so all, oops, no. Undo, undo, undo. Where's my undo button? Yeah, there you go. Did not mean to do that. I had already clicked it, and it didn't click. So I thought it did. Okay, there we go. Now, so all of these are the non-metals, right? Every bit of this, except for the ones that we're going to put stars with. And yes, this one is also one of them. Okay, there we go. All right, that works. And then the metalloids, I'm just going to put little stamps on them. And I know you've seen the metalloids, but just to remember. All right, so these are metalloids. This one, this one, this one, this one, this one, this one. Okay, so those are your exceptions. I couldn't take them out that easily, so I'm just gonna leave them there. But those are metalloids, and they basically have properties of both metals and non-metals, so it works. Okay. All right, so that's everything we needed to label as far as this periodic table goes. I mean, the ones that I can do here. Now, the other ones that we need to label are liquid, solid, and gas. Okay, so most of these are solids. And I'm going to go to another periodic table. Oops, not like that. I'm not. I just put a star there. I'm going to go to another periodic table. Yeah, see, that stays on there. So I need to erase all of that. So if you all got it, I can move on. Yes. If not, I'll return to it.
Yes, you can move on.
Okay, so I can clear all of it. Okay, good. All right, so we want a periodic table with states of matter. Okay, and here we go. And this is the best one because they're all clear. You know, it's very clear which one's which, I think. All right, so you can put an L for liquid, an S for solid, or just do colors, however you want. But here they are. Here are the ones that are liquid and gas. You see, there's the key. So anything that is yellow in here is a gas, and anything that is blue is a liquid. And of course, all the other ones are solid. So yeah, mark those so that, see, the noble gases are called gases for a reason, right? You notice that the new one, they're unknown. See, all of these new ones, it says unknown. So that's why we don't have them in our periodic table. We just leave them alone. But they are solids. The unknown part is what actual shape they make. They're crystals. So you notice right down here, there's a simple cubic, body center cubic, face center cubic, hexagonal, orthorhombic, rhombohedral, tetragonal, monoclinic, and unknown. Those new ones are unknown. So, but everybody else. All right, mark those. Let me know when you're done, and we'll move on. I'm sorry. Just getting ready for the next one. Right? We now need to mark the ones that are man-made. So elements that are man-made, hence also known as synthetic. So, okay. What? Let's look at images. That one's okay, but there's one that's better. That does a much better job. Oh, there we go. That one right there. That's the one I like because it's quite obvious. Okay, so we're going to go to that one. As soon as we get to it, we'll make it bigger. Okay, there you go. So basically, it's all of the bottom row, starting with Rutherfordium. One little upper there, technetium is a man-made element. And then all of the they're known as transuranium elements because they're after uranium right here. Hold on, right there. This one, that's uranium. So transuranium elements are everything after that on that row, on the actinides. So those are all your synthetic. Yes, we have contributed a lot to this periodic table. Man has. And we do have names for them already. And those are not giving names, but they're saying they existed. They've been named now, every one of them. Including that last one. Right. You guys have those? All right. The last time that we're going to look, the last one we're going to look for is a periodic table with radioactive elements. There we go. And that's the one I like to look at because it is much better. As far as you can see which one's which. And if you notice, all of the man-made elements are radioactive, but there's others that are naturally radioactive. So that's kind of one of the reasons why we're doing this, so that you know which ones are already radioactive. There's just a few more. And that's basically all that we're doing with the periodic table today. Oh, and if you want to, you can fill in the blanks on the periodic table that I gave you guys. Just add all the extra elements starting with DS, with Stern Stadium, and go all the way to OG, which is organism. On the very bottom. Just so that you know that they're there, because they do exist now. Okay. So you should have marked everyone that's synthetic and now all of your radioactive elements. And you saw how I found them, so you can just look for them if you want to take another look at them later. All right, so we are going to go to another PowerPoint today, and that one is known as Matter Is, I think. Did we do that one already? We do all the physical and chemical changes, or no? Somebody who remembers.
Let us see the PowerPoint. Maybe we can.
Okay, sure.
Complete.
I'm getting there. I just It's got to get there. Let's see. See, it takes a little while for it to load. There it goes. Okay. Right. So the point starts with, I think we did, but there's something else we need to do if it's not that. I do believe we did. Oh, come on. That's wrong. There we go. All right. That would be this PowerPoint right here. Matter is.
Yes, we did.
We did do that one, right? I thought so. Okay, so we finished that one. All right. So the next thing we need to do actually is the kinetic molecular theory. That's and remember, theory in science is a big deal. It's not just I have an idea. Like when we say I have a theory, no, this is an actual thing that they've done a lot of studies. All right, so I created this diagram for everyone to understand it a little bit easier. Basically, what you have here is how things behave, okay, as they change. There we go. That's as good as I wanted just to show the things that I need to show. Maybe a little bit bigger. There we go. All right, so with this one, what we're going to look at, obviously, is all the states of matter and what it requires to get there. So that's why it's called the kinetic molecular theory, because kinetic energy, as you know, is the energy of movement, right? And temperature is the measure of that average kinetic energy in that system. And in order for you to be able to move, you have to have distance between, whatever you're next to and you, right? So that's all together. Okay, so let's look at this first part. So when you are solid and you are melting, right? There's the word, to become a liquid. This is what's going on. Your temperature is increasing, right? Because see how it's going from low to high? Your kinetic energy is also increasing because now you're not fixed anymore and you can do more than vibrate. You can actually just slide molecule, through the molecules. And the distance between the molecules, again, is also increasing, all right? So as you're evaporating, so you're going from a liquid to a gas, you're also getting more energy, gaining energy. So that means you're absorbing it, because energy is not just anywhere. It is finite. It's a number that exists, and all you can do is either it cannot be created or destroyed. It's just transformed. So all the energy that's ever been in the universe is still there. We just use it in different forms. All right, so the liquid becoming a gas is now gaining more temperature, more kinetic energy, right? And the distance between the molecules is increasing. That's melting, evaporation. Now, if you're going the other way, you're condensing. Now you need to drop off some of that energy back into the environment. See, this is what I was telling you. Now you're giving it back. And you're going to go from a gas, which is at high temperature, like think of water vapor. That's very hot, it burns. And you are condensing into a liquid, which a liquid is a little, these particles are far apart, they're hot, and there's a lot of movement. Whereas in a liquid, the particles are not so far apart. They are not as hot. They're actually room temperature, you could say, and they have a lower kinetic energy, but they still have quite a bit of kinetic energy. They move. And then from a liquid, you go to a solid, and it's called freezing, right? And that freezing is, again, dropping some more energy out into the system. And the solid is now in fixed position, and it is a low temperature low kinetic energy, very small amount of distance between the molecules. So that's how it works. Now, there probably are two words you've never heard before, or maybe if you've heard them, maybe you forgot them. When you go directly from a solid to a gas, it's known as sublimation. If you've ever seen dry ice sublimates. It goes directly to a gas. It doesn't go through a liquid at all. It just looks like it's smoking directly, right? Well, that's the vapor of it. It's actually changing. And then you have also seen what is known as deposition, which is when you go directly from a gas to a solid. And that is every morning when it's cold, you see frost on your windshield. That was deposition. It was the water vapor in the air falling straight into a solid and falling out of suspension onto the ground. All right, and that requires a lot of energy being given up. So certain things can do that, but not everything can do that. So they have to have a transition, a middle transition, right? Like solid, liquid, gas. Well, but some of them can go directly. Okay, so that's the thought. Now, intermolecular forces. This is the one thing that is totally different. You notice that it goes the opposite way. But basically, all intermolecular forces are, well, the word kind of tells you inter is between and moleculars is between molecules. So if you have molecules that are interacting, like they say, this is water. So yes, they are interacting. The intermolecular forces are at its highest when it's a solid. Well, think about it, because they're attracting each other, right? So if you're attracting each other, you're going to be as close as possible in fixed positions because you're not allowed to move because you're so attracted, just like a magnet. All right. And then those forces loosen a little bit to become a liquid, but they're still very much present. And now they're a little looser and lessened, and you can just move past each other, kind of like that's what a sliding movement does. And that's why water pours like a stream and not a different thing. And then the last thing is gas. When you become a gas, those intermolecular forces have been pretty much eliminated. So they're, no more. And that's how that works. And the opposite is true when you're becoming from a gas to a solid. Intermolecular forces begin to increase so that you can become, so you can become a liquid. This thing I didn't mean to. Okay, so you can become a liquid. Yeah, I need to put it back. Like I said, I made this, so there we go. So you can become a liquid, and then they increase even more as you become a solid. So that's the whole kinetic molecular theory. So basically, as you're going from left to right in this diagram, you are absorbing energy into the system. So into the system means the ice cube, the glass of water, the whatever it is, right? And you're releasing it out into the environment when you are becoming a solid. So from right to left. So that's how that works. All right. So that's your kinetic molecular theory of matter. Now there is another, don't say because I didn't really do any changes. Sorry, that's not one that we want yet. Don't save, I was just looking at it. All right, so the next one that we're looking at is a phase change diagram. All right, this diagram is the best one I have found so far. And it is a temperature versus heat. Heat is a transfer of energy. So when you are transferring energy, that's kinetic energy, the temperature will increase, which makes sense. Okay, so here is a diagram of how that happens. So you are ice down here, so you're at 0 degrees, right? All of through here. until you hit 273 Kelvin, which is 0 degrees Celsius or 32 Fahrenheit. All right. So you are right here, and this is what is known as your boiling, your melting point. That melting point is also can be measured and is known as a heat of fusion. So the amount of energy that it takes to change 1 gram of water from a solid to a liquid, or a liquid to a solid, it goes both ways, is 80 calories per gram. Okay. And it's always by gram because, it's by mass. All right. And then you've got, if you notice the steep slope right here, that indicates that this change happens rapidly. And it makes sense because, and this also happens rapidly. It also makes sense because you're not breaking those intermolecular forces. You're just weakening them just a little bit. They dominate here, though. This is the domination of, they're the highest. And then you've got ice and water mixture right here. And once you get up here, right, right here, once you get up here, it's all water, right? All of this, but they're increasing in temperature because you're gaining more and more, it's transferring more and more heat into itself. And you notice the slope is not as steep because it happens a little less fast due to the fact that you have to change the intermolecular forces completely. You have to weaken them so much that you eventually will break them. And look how long it takes. This is what is known as a big transfer of heat that's going to happen. In the heat of vaporization, it's 540 calories per gram. It's a big difference between the heat of fusion to the heat of vaporization of water. And then and this is also known as your boiling point, just the temperature part, right, at which it happens. And then all of this heat exchange finally results in the breakup or intermolecular forces and becoming a gas. So all of that works together. All right, now let's look at a little bit of a different one and go back to it. Let me see. I think I can just go back. Yeah. All right. And this is a phase changes chart. This is a little different because the criteria that we're looking at is different. You notice we're looking at temperature and time. Okay. But the steepness of the slopes is still there. All right. So we are looking at the freezing point. You notice that we're not really looking at the amount of heat that is transferred. We're just saying that we're adding heat as we're going up, which we are. That's what is energy transfer. And there's melting point. Each one of these plateaus is a melting or a boiling point, or a condensation or a freezing point, depending on which way you're going. And a solid is mainly here. A liquid is mainly on this slope, and the gas is mainly on this slope. This right here is a combination of both. Okay, all the slopes are until the last molecule is transferred. All the heat has been absorbed, then it becomes a gas. Okay, and that's how it works. Or the last molecule here has absorbed enough energy to become a liquid, then it breaks that and it can keep rising. But in the meantime, the temperature is held constant because there is no heat exchange going on necessarily. Okay. All right. And that's how that works. All right. Let's stop this share. Because, no, actually, I don't want to stop this share. I want to go somewhere else. All right. So we know all about this stuff. Now we can actually look at our Connect, and you can see that you can take your test already, even though we don't have yet finished the the essay question. So don't do the essay question yet, but you can actually take your test already. And I'm going to show you the picture. Oh, Lord, where are you? I'm getting there. It's just, I don't want to pass it, and I passed it anyway. There we go, the connect. There we go. I'm going to go to connect now, and I'm going to show you that last one that we were doing, that assignment 1, chapter 1, that you can actually finish it now. You are ready. So chapter 1 assignment right here. We're going to look at it as a student. And we're going to just skip around, of course, because we're not going to do the whole thing, since you already know that you could have finished all of the math part. But okay, so here a solid has a fixed shape, right? That does not conform to the container. See? A liquid has a varying shape because it is not set, that does conform to the container. And it says that is a liquid does form an upper surface. So does a solid, by the way. But a gas has varying shape again, right? And does not conform to the container. Oops, varying didn't stay. Okay. And thus it does not form an upper surface, because you cannot put something on top of the top of a gas, because there is no top of the top of a gas, but there is a top of water, right? So you can actually have a boat floating on it or whatever it is. All right, so let's go. Oh, check the work, and it should be correct. Oh, did I put does not? Oops, I meant to put does. See, that was me. That should be does right there. So that should be that one. Anyway, we're not going to go there, but I don't know why I put does not. It does not. Okay, so this is the part that's going to be a little weird for you. Okay, so if you look at it, right, you can see that these are all separate, right? And we know that all elements are represented by a symbol. And that symbol needs to start with a capital letter, and it may or may not have another letter. But if there is another letter, the letter has to be a lowercase. So anything that is representative of an element but by itself is going to fit here. You see that? You notice I skipped the HF and the CO because they don't meet the lowercase that I was talking about. They're not elements, they're compounds. And none of them are doubled. Okay, so that's that. Okay, now this one is the same element, but 2 of them. So N2 would be one of those. H2 would be one of those, right? Cl2, if you see another one, let me know. O2 and F2, right? That's it, I think. And then this one is one element and another element, but that's just 2 elements. So one of each. So CO, HF, SO, and that's, oh, NHI, here's another one. Okay, this one has 2 to 1. So anything that is SO2, for example, right, 2 to 1, anything with 2 to 1, doesn't matter which one's the 2 and which one's the 1, because we're just representing it. All right, the rest are none of these, because we don't have anything with 3 and 1, or 4 and 1, or 2 and 4, or 1 and 3. So no. All right, so let's check the work. And sorry about that first one. I just was not looking closely. Right? See, there you go. So you can do these. All right, let's look at the next one. All right. All right, here it says elements, compounds, or mixtures. And we did this just recently. So you know that this is a pure element, right? This is a mixture of 2 elements. This is a mixture of 2 elements also. This is a pure element here. Another pure element. Yep, I know you see three, but they're all the same. This one, however, is a pure compound. See how you got the two blue and the one yellow? This is a mixture of compounds. This is, let's see, see how there's one of these, two of these that have two reds and one green. So this is a mixture of compounds also. This is a pure compound, right? And this is the only one that's a mixture of element and compound. All right, check the work. Let's see if that's right. Should be, but oh, this one. Which one did I put in there? Which one did I put in there? That is not. It says no. That one? Oh, yeah. I don't know why I put that one in there. Oh, my Lord. That goes in there. I guess I was dragging things and not paying attention. But yeah, that would have been a mixture of not two elements. That would have been a compound, period. That's a pure compound. I don't know why I put it there. Okay, so let's put it in the right spot. Okay, so this one goes here. No, not you. You. You go back this way. This one. Nope. Okay, let's see. Let me just put this one. There we go. And then that last one should go here. All right, there we go. That's how it should have been. I wasn't looking close enough, but there you go. That's it. That should all be correct. Yeah, see? All right, so let's go to the next one. And I was just doing this too fast and it probably dropped off. Again, compound, element, or mixture. So you've got the same thing to do. Except here, what they're trying to do is they're trying to show you the state of matter also. But basically, if you can make it bigger and you can see, right, that is just one kind, then you know that's an element. That is two different things in a fixed ratio. That's another element right there, but it's a solid. This is a mixture of two elements or whatever. This is a pure element there. This is a mixture because it's got two things on it. This one's also a mixture. This is a pure element. This one is a compound, and this one's also a compound. And that should be it, right? You can kind of see them when you look at them closely. See, that should all be okay. Yeah. All right, so next. All right, chemical or physical changes. Okay, this one's a little different. You got to make sure that when you're looking at it, it hasn't changed. I mean, it has changed in state, obviously, because this was a gas and this is a liquid. So that's a physical change, right? This one, same physical change, right? This one, see, you can see there's a difference. Now here you have a blue and a yellow, and here the blue and the yellows are separated. So that's a chemical change. This one's also a chemical change because they were bonded and they're not anymore. So is this one, they bonded, and this one too. Okay, and that's it, right? That's all of them, I think. All right, let's check the work and see. I know sometimes I work faster than my brain lets me realize that I put it in the wrong place. All right, so here you've got words and you know these, so you can just do those. I'm just kind of showing you more of the visual ones. All right, here, chemical. Okay, so baking a cake, that's going to be chemical, right? So you're going to put it, that's physical. That's physical. And look at the last one. They're showing you a chemical change because you can tell that something's changing there. They're not the same. The products and the reactants are not the same. So you check your work and you're good. If not, you can always go back like I showed you. All right. And then this one, see this one, you just say physical or chemical like I did before. We're not going to go over all of them. Oh, sorry, I meant to say next. All right, that one we've done. Okay, this is the one you don't know about. Okay, you remember how we labeled that periodic table with the 1A, 2A, 3A, 4A? Okay, so this is how this works. Metals, and we also have metals and non-metals, so all of this works into one. Metals lose electrons. So when a metal loses electrons, let's say we have sodium. Okay, so sodium, and I'm just going to write it here. I'm going to do a quick annotation so that you get this one really quickly. Okay, so sodium normally has 11 electrons. And that's, how do we know? Because there's a number 11 above it, right? But when sodium becomes an ion, since it is in group 1A, that means there is one electron on the outer shell. And since it is a metal, it is going to lose electrons. And how many? Based on this, 1. Okay? So then sodium now becomes a positive. Why a positive? Well, now you only have 10 electrons. Okay? And electrons are negative and protons are positive. So see here, there's no charge, right? So that's a 0. That's why we don't put a charge, because they're balanced, electrons and protons. And you notice I put P plus and E negative, just so that. All right, and now here, the electrons never, the electrons can change, but the protons can never change. So if you were to mathematically subtract those two, you would see that you would get a plus, right? So that's why it becomes a +1. So sodium, if I drag it in there, it's going to be a +1. You see that? Calcium is in 2+ because it's in 2A. All the metals, we're just going to do all the metals. Rubidium is 1+ because it's on the first column. Metals. Lithium, +1. Strontium is a +2 because it's in 2A. Magnesium, another 2A. Potassium is a +1. Okay, we didn't talk about aluminum, but aluminum is in 3A and it is a metal, so it goes in 3+. And barium is a 2+. All right, and cesium. Cesium's the last one of these. It goes in here. Okay, now let me clear these, and now let's look at the non-metals. Non-metals, metalloids, it doesn't matter. Okay, so when, and hydrogen's an exception because it's on this side, so it actually becomes a 1+ also when it loses that electron, because it only has one electron. Okay, so now let's look at iodine, for example. Or let's do fluorine. Fluorine's easier because it has less electrons. So, all right, so fluorine. Oops, I need my writing thing here. Okay, so fluorine, right, is a 9, right? It has 9 electrons because that's what it says. It has 9 and 9 protons. Okay, and fluorine is also in group 7A, which indicates that you have 7, and I'm just going to draw them here. 7 electrons on the outer side of this guy. Okay, so this is the one lonely one. Okay, so as you can see, instead of losing 7 electrons, which is a lot of them, metals, non-metals, these are non-metals, and they gain electrons. And how many? Based on this, they want 8 electrons around them. So what they want to do is gain 1. So plus 1 more is 10. No, sorry, not here. Plus 1 more is 10 electrons. Okay, so it becomes 10. Now, if you subtract those two, you can see that's a negative charge, right? All right, so the negative charge that is going to be for anybody that's in group 7 on this one. All right, so we're going to drag all the group 7 ones into negative ones. That's fluorine, iodine, chlorine, and bromine. All right, that's fluorine. Now let's look at sulfur and oxygen. Okay, so let's clear those. Sulfur and oxygen. Let's do oxygen for easier thing. So oxygen has 8 electrons and 8 protons in its normal state. If it becomes an ion, it becomes a 2 negative. Why? Because oxygen actually has 6 electrons on the outer shell. How do we know? Because we have group 6A. See, that's why the groups are necessary. So you just have this, you have 2 single ones. And it's obvious that it wants 2 because remember, everybody wants 8 electrons on their outer shell. He only has 6. So by gaining 2, it becomes a 10 electron and still 8 protons, right? That doesn't matter. So again, it's a -2 because positive minus negative gives you -2. So oxygen and also sulfur, which is also in group 6. And then nitrogen, we can do the same thing, and it's in group 5. Why? Because nitrogen has 5 electrons, right, on the outer shell. So to gain 3 would make it 3 negative. And there you go. And that's all of that's how you sort these out, okay? That's why it was so important for you to have the 1A, 2A, 3A, 4A, that kind of thing. All right, so these are all what is known as representative elements, and that's one thing we did not go over, and I'll show you in a minute, all the representative elements, but I call it the tall columns. So you know what the tall columns are on the periodic table? The 2 on the right, on the left, and the 6 on the right? That's it. Those are all your representative elements. All right, so let's check the work. Should be correct. Yeah, see? So that is how you know where to put them. And this one we've done, so let's just keep going. I think all of these we've done already, but let's just keep on just to see. Yeah, this sig figs, precise, accurate, we've done that one too. Okay, I think that's all of them, pretty much. But we'll see, just to check, make sure that we have pretty much an example of every single thing we're doing today. Yep. Okay, here we go. Nope, we didn't finish yet. Okay, so here you just need to put chemical or physical, right? Right. Obviously, that's a change in state, so that's a physical change. This one, on the other hand, is changing completely, so that is a chemical. This one is just a change in state if you look at it closely, so it's a physical change. But this one is a chemical change, right? So it's a chemical reaction. Check the work, that should be correct. Yeah. All right, next. Let's see, there's another one like that. Yep. All right, same thing. I'm not doing that one, but you know how to do it. And then this one's a little picky. This one's tricky because the number, see where they are? So you got to look at that. Okay, so looking at this one, you got all blue and some red. Okay, so this is a physical change. Actually, no. This one, no. This one's a chemical change because even though you have some leftovers, you formed a compound. You see that? All right, this one, see how they're separating the two? So this is a separation like you're going to be doing, but it is a physical because the things are still what they are, right? Then this one over here, 3, you notice this is a chemical change because you are separating the 2s into 1s. So this is a chemical change. This one over here is a physical change because you're just basically freezing these. And then this to here, this one to this one, this is another chemical change. You can really see that. Okay, so we've done all of them, right? And you can check your work. So you see how each arrow is pointing to where it wants you to determine what it is. And there you go. All right, and that's the last of it. So as you can see, we can already do every single thing that is on here. And I checked the test to see, and yes, you can pretty much take it because all of this has been done. Now the mixture separation, it's important to do, and we'll go over that next time. And then you'll be set, but you can actually take the actual test today if you want. And I have actually given you 3 chances for you to take it. So, and you have until, the 15th, I think it is, to take all 3. So if you want to take it one time and see how you do, and then, see where you missed, and then take it again and do better. And by the way, it is the best one of the 3 that you'll get. So if you make, let's say, just to say something, I'm not expecting you to make a 70, but let's say you make a 70, and then you take it again and you do like an 82. Okay, now that's a better grade. So that one is the next one. And if you feel like taking it again, you make a 90 something, there you go. That's your A. Okay. So that's how it's done. All right, that's pretty much all I had for you today, unless you have questions or anything else. No questions. All right. Well, you all have a great weekend, and I'm really hoping I'll see you Monday in person.
Okay, you too.
Okay, take care.
Bye-bye.
You too.
Bye. Bye-bye.
Bye.